Here goes the rest of section 12, which, as I said at the end of the last recording, revolves around the ideal gas law, PV equals nRT. But before we get to that, we have to define all the things that are in the gas law, starting with temperature. We're leaving the field of mechanics, by the way. We've been doing mechanics since the first day of the course, and we're not quite completely done with it, but anyhow, the temperature of a substance, what it's actually telling you physically is the average kinetic energy of its molecules. Whether it's a liquid, solid, or a gas, molecules of a substance are constantly moving around. In the case of a gas, it's like the air in this room. Each molecule is just shooting around, following kind of a random path. If you watch one particular air molecule, it goes across the room for a bit, it bounces off the ceiling, then it goes down and it bounces off the side of that table, comes over here, bounces off another air molecule, and just kind of goes ping, 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 with an average speed of around 1,000 miles an hour. That's just an average. There's a whole distribution of speeds, and a lot of them are going significantly slower than that, and a lot of them are going significantly faster. As another example, in the case of a solid, it's a vibrational type of motion. Each molecule behaves as if it's attached to its assigned position by a little spring, and it vibrates back and forth. The higher the temperature, the more vigorous the vibration. If the temperature gets too high, the crystal lattice basically just rattles apart, and that's called melting it. But anyhow, whatever state of matter it is, the things are moving around. The higher the temperature, the faster they move. And what the temperature is proportional to is the average kinetic energy of the molecules. So that's what temperature is physically, as opposed to just, oh, that feels hot or that feels cold. We're not going to get into the exact details because there's only so many days in a semester, but I would refer you to the textbook. There's a whole chapter on the kinetic theory of gases that would go into a great deal of detail in the case of a gas. And there's other references for solids and liquids. But anyhow, temperature scales. As you're probably aware, the Celsius scale, actually, these haven't been the official standards for the Celsius scale since the 1950s, but it's still a convenient way of explaining it. The 0 degrees Celsius is the freezing point of water, 100 degrees is the boiling point. This assumes pure distilled water. It assumes standard atmospheric pressure, because both of those things, like if you go mixing water with antifreeze, it freezes at a significantly lower temperature. Or salt, salt water has a lower, that's why they put salt on the roads, has a lower freezing point. But pure distilled water, atmospheric pressure. Now, the Kelvin scale uses the same size degree as the Celsius scale. If you had one thermometer for each scale and put them next to each other, the marks would be the same distance apart. You just start counting in a different place. The Kelvin scale puts 0 degrees at the lowest possible temperature. Why is there such a thing as a minimum possible temperature? Well, it's simplest to think of it in terms of an ideal gas. I'll explain exactly what that means in a few minutes. But if you were to think of the air in this room as being an ideal gas, well, I just got done saying the temperature corresponds to the kinetic energy per molecule. If you heat the air up, you're adding energy to the molecules, making them move faster. Heat is a kind of energy. By the same token, cooling it off amounts to drawing energy out. Well, what if you were to draw out so much thermal energy that the gas molecules were just laying around on the floor at rest? you're not going to get them to go any slower than that, okay? There is no energy left to extract at that point, and that would occur at negative 273.15 degrees Celsius. Now, having said that, I'm probably tired of looking at that. Occasionally somebody takes this course who goes on to become a physics teacher. I could name several I've had over the years. And I don't want somebody to walk out of here and then spend the next 40 years telling thousands of people molecular motion stops at absolute zero, because it's a lie. Yes, the motion of the molecules of an ideal gas would stop at absolute zero. But an ideal gas is one of those approximations you've heard me talk about in here before. It goes right there in the same category with frictionless surfaces and massless rods and so on. It's a little game of let's pretend we can play to make calculations simpler, and in a lot of cases it doesn't really affect the accuracy within the level we care about. But any real substance does not remain a gas all the way down to absolute zero. They all liquefy, and almost all of them become solids. The only exception I can think of is helium. It takes about 10 atmospheres worth of pressure to get solid helium. At atmospheric pressure, it would be a liquid at absolute zero. But the behavior of liquids and solids is considerably more complicated than that of an ideal gas, okay? In a solid, which is what most things are near absolute zero, you have a vibrational type of thermal motion. The molecules are basically harmonic oscillators, at least approximately. Oscillators have energy levels, kind of analogous to the energy levels you might be familiar with in atoms from chemistry class. The ground state energy of a harmonic oscillator is not zero, okay? So the more accurate way to describe absolute zero is to say that's when you have removed all the thermal energy which is removable. You have every molecule in the solid in its ground state, its lowest energy level, but that is not a state of rest, okay? And well, we'll get a little deeper into that story if you take Physics 133. But anyhow, talking about an ideal gas at least gives you some feeling for why there should be such a thing as a minimum possible temperature, okay? So that would occur at 273 below zero. And, you know, why have a scale with negative temperatures? Why not just start at the bottom and count up from there, and that's the Kelvin scale. So that's a few words about temperature. Another thing that's involved in the gas law is pressure. Pressure is the force per unit area. Sometimes what matters is not so much the total force that's present as how that force is distributed. Is it concentrated into a small area, or is it spread over a big area? I kind of like this picture here that I clipped out of something once. You've got a person. We won't make any gender assumptions here, but whatever kind of person this is wearing one shoe with a fairly regular heel on it, and one with this really small spike heel. And presumably they're not leaning to one side or the other, so that you have pretty much the same amount of force bearing down on both of them. Well, this person is standing on this like foam rubber mat. Notice how much farther the spike heel pushes through the mat compared to this one. Same amount of force, But here it's concentrated down into a much smaller area, creating a much higher pressure. So sometimes what matters is the force per unit area rather than the total amount of force, which is the same on both of these heels. So I should write some of that down for you. Pressure. Force per unit area. To be precise, F is the magnitude of the force. Pressure is a scalar. It has no direction, okay? Because, like, consider the air pressure. I've got this book here, okay? The air in this room pushes down on the top of the book, but it pushes up on the bottom of the book, and it pushes horizontally on the sides of the book. And if I held the book this way, it would push at an angle. The air pressure has no direction associated with it. So pressure is a scalar. So anything about the force's direction, you want to ignore that. As for where the force that I'm talking about comes from, the force is due to, in the case of a gas anyhow, not exactly when you're talking about somebody with a spike heel standing on a rubber mat, but if you're talking about pressure from, you know, like air pressure, or even in a liquid, this force is due to molecules bouncing off the surface. I mentioned a few minutes ago that the air in this room, for example, is a very large number of little molecules kind of shooting around every which way like the popcorn inside of a popper. And that means, for example, this piece of paper I'm holding, there are air molecules constantly bouncing off of it, down here on the bottom also, a few on the side even, you know, it's just a thin little sheet of paper. So there's a constant bombardment on any surface that the gas touches. Anybody who's ever been hit by a baseball can tell you that having something bounce off of you like that delivers a little kick, okay? So since there are constantly air molecules okay, there was apparently a little glitch in the connection there. I don't know if I'm going to end up with one recording or two. And I'm not sure exactly where that cut out a moment or two ago. But hopefully, well, maybe I better repeat a few things in case it got lost, because I wasn't looking at the monitor every second. It is definitely recording now. Pressure is force per unit area F is the magnitude of the force because pressure is a scalar, it has no direction. And the source of that force is the fact that the gas molecules are constantly moving all around, and therefore any surface like this one is constantly bombarded by molecules that are bouncing off of it. And those impacts create the force that are responsible for the gas pressure. So if anything got lost there, hopefully that covers it. And A is the area over which the force is distributed. Units. They're actually the only ones we will concern ourselves with in this course are, first of all, the SI unit. In the SI system, force is measured in newtons. Area would be measured in square meters. A newton per square meter is given a name of its own. It's called a Pascal. Abbreviated PA. And then there are also some non-SI units that I might mention now and then. Pressure as a unit of pressure. It's probably more meaningful to tell somebody that the pressure inside of a boiler is than to tell them that it's, what would it be, 3 megapascals? Something like that. So sometimes, you know, pressure in atmospheres. There is that I have to splice together or something like that. Pounds per square inch. Standard atmospheric pressure is 14.7 pounds per square inch. Now, standard there's a barometer in the chemistry lab that I look at fairly often because there's some lab experiments we do where we need to know the current atmospheric pressure. That reads in centimeters of mercury. Standard pressure is 76 above sea level here. But standard pressure, average day at sea level, which is also again, here in Batavia, atmospheric pressure is usually around 97, 98, 99 kilopascals. A kilopascal, of course, is 1,000. A kilopascal would be something you'd have to convert into pascals, just like atmospheres or anything else. This is on your formula sheet in the table of conversion factors where you can look it up whenever the mood strikes you. I'm just going to read it off to you instead of moving the camera to show you one line of writing. It's section 12, problem 4, and it says, find the force the atmosphere exerts on a window with an area of 7,000 square centimeters. 70 centimeters by 100 centimeters being just about the size of the larger window in my office, I believe is where I got those numbers from. So all there is to this, just a little exercise to reinforce the definition of pressure. Pressure is force per unit area, therefore, multiply both sides by A, force or pressure times area equals force. And the question tells us the area. And since the question says nothing to the contrary, we'll assume standard atmospheric pressure. You know the two things, you just multiply them together, except as with most things, you have to be careful of the units. Standard atmospheric pressure, 101 kilopascals would be 1.01 times 10 to the 5th Pascal, 1.013 if you wanted to take it that far. (101,000 pascals). A pascal, once again, means a Newton per square meter. The area given in the question (7,000 square centimeters). Well, of course, square centimeters isn't going to cancel with square meters. So you might be tempted to move the decimal 2 places because 1 meter equals 100 centimeters. But you would not be correct. Notice that centimeters to the first power does not cancel with centimeters squared. You got to do that. There's 100 linear centimeters in a linear meter, but there are 10,000 square centimeters in a square meter. And for that matter, there's 1,000,000 cubic centimeters in a cubic meter. So you have to move the decimal 4 places. If you would like to see a geometric explanation of that rather than an algebraic one, square meter is about that big. That's about a centimeter right there. And that's a centimeter. So that right there, that little tiny square down in the corner, that's a square centimeter. Notice that if I felt like drawing more of them, there are 100 of those just in the first row. By the time I have filled this entire 100 by 100 square, I'm going to have 10,000 of these little guys. Okay, so move the decimal 4 places, and that is the one trick that would catch a lot of people in this question. So the force that atmospheric pressure exerts on my window comes out roughly 8 tons. Should have had this back over here, shouldn't I? The reason it doesn't blow the window out of its frame is because, yeah, you've got 8 tons pushing on one side of the glass, but you've got exactly the same 8 tons pushing back on the other side of the glass, and it exactly balances out as long as you've got an even amount of pressure on both sides. Next thing it says is absolute versus gauge pressure. Imagine you're driving along one night and you don't notice until it's too late that there's some ragged piece of sheet metal that somebody left in the middle of the road, and you run over it and it tears a big gash in your tire. Well, let's just say hypothetically that you've got a tire gauge in your glove box and you, for no really good reason, decide you want to measure the pressure in this tire, which now has a hole that long in it. If you do that, you'll find the gauge says 0. But think about it. There is no way a tire with a rip that long in it can hold a vacuum. You don't have 0 pounds inside of that tire. You've got almost 15 pounds per, actually this altitude probably closer to 14 pounds per square inch in there. But the gauge doesn't say 14, it says 0. Because the way most pressure gauges work, there are some exceptions, but the typical pressure gauge anyhow, does not exactly read pressure itself, it reads differences in pressure. If you put a gauge on your tire and it says 30 pounds per square inch, that means the pressure inside is 30 psi more than what you have outside. Well, outside you've got maybe 14, means you've really got 44 inside the tire, even though the gauge says 30. Okay, so that's the difference between absolute pressure and gauge pressure. Gauge pressure, like you'd read off a gauge, tells you the pressure relative to the surrounding atmosphere. Absolute pressure means the total pressure that's there relative to a vacuum. And to convert from one to the other, you would add or subtract atmospheric pressure. So absolute pressure, where am I aimed? I should probably be a little further over that way. The absolute pressure equals the gauge pressure plus 1 atmosphere. Absolute, again, meaning pressure above a vacuum. For purposes of a course like this one, if you hear something just called pressure, without anybody specifying absolute or gauge, they're talking about the absolute pressure. This can be a little different than other situations. You know, if somebody's talking about the pressure in your tires, they're probably talking about the gauge pressure, even though they don't specify that. But for our purposes anyhow, if I mean gauge pressure, I'll either say gauge pressure or otherwise tip you off. You know, the question might say a pressure gauge reads and some number, something like that, that tells you it's the gauge pressure. If it just simply says the pressure is, you can assume I mean that. Same with the textbook. Same with just about any other textbook. pressure above a vacuum, and this is the pressure above atmospheric. Okay, so that's background information because the gas law involves absolute pressure and absolute temperature. If you're given degrees Celsius, you have to convert to Kelvin. If you're given gauge pressure, you have to convert to absolute and so on. So now, the next thing it says is, well, before I get to the ideal gas law, maybe I should explain what is an ideal gas. An ideal gas is one whose molecules do not, first of all, take up any space. We are assuming that the atoms making up these molecules have a radius of 0. They are point particles. So like, an oxygen molecule, you have a point-like oxygen atom there and another point-like oxygen atom there, and does not occupy any space, just little point-like masses. The other assumption is that these molecules do not interact with each other in any way. There are no, except perhaps by running into each other every now and then, but there are no van der Waals forces or anything like that going on. No forces other than collision forces. They do not attract or repel each other in any way, which of course would keep them from ever coalescing into a liquid. Real gases behave like an ideal gas when they are thin. The air in this room is described very nicely by the ideal gas law, but as with any of the other approximations you toss around in an introductory course, you take things too far and the approximation breaks down, okay? You can't always assume that the floor is frictionless. You can't always assume that liquids have no viscosity, and so on and so on. Okay. So here's the big moment I've been building up to for the last, I don't know, half hour or whatever it's been. Should probably have a little drum roll or something, but here is the gas law. The equation of state for an ideal gas, PV equals nRT. P for pressure, T for temperature, and as I mentioned a couple of minutes ago, both those things have to be absolute. Commonplace, I use some red ink, as the question gives you the temperatures and the temperature in degrees Celsius, and you forgot to convert it to Kelvin. Likewise, gauge pressures have to be converted to absolute. N, that's how you tell the equation how much gas is in the container. That's the number of moles. The behavior of the gas turns out to depend not so much on the gas's mass as on how many particles that mass is divided up into. But if we just worked with the number of molecules in the container? Well, you could do that, but it's a really big number. It would always be something times 10 to the 24, 10 to the 25th. And that's no fun. So what they tend to do is count the molecules in moles, which you've probably heard of in some chemistry course. But in case you're a little rusty or have somehow managed to avoid taking chemistry, the word mole means 6.02 times 10 to the 23rd in exactly the same way that the word dozen means 12. You can go into the bakery and say, I want 2 dozen donuts, and the baker knows to give you 24 donuts, okay? And if you went into the bakery and tried to order a mole of donuts, well, the problem there is that they wouldn't have that many donuts, but it's the same idea. As for why this particular number and not a different one, that's a chemistry thing. I don't actually remember off the top of my head. I'd have to look it up. If you're really curious, take chemistry and they'll probably explain it to you. So that's N. I don't think I was even gonna, yeah, you know what, I should label the V. I just kind of skipped over that. That's just volume. How much space does the gas occupy? So I probably should have written that down first, like working our way across here. P for pressure, V for volume, N is the number of moles, T is the absolute temperature, R is the proportionality constant between all those other things. Usually just called the gas law constant. The universal gas constant. In the units we'll be working in, .314. That's joules per mole per Kelvin. Technically, you're not supposed to say degrees Kelvin anymore. Oh, it was about 20 or 30 years ago they changed that. It's now just kelvins. It's still degrees Celsius when you talk about that scale, but on the Kelvin scale, it's just kelvins. For something a little closer to reality, I'm not going to write it down or anything because it's not an official part of this course, but I do on the bottom of the page here have jotted down van der Waals equation of state, which contains some correction factors to, you know, for when those assumptions I made over there cannot be made. You know, if the molecules do attract or repel each other, there is a somewhat more complicated equation of state that you can use, but I'll just throw it out there that exists. It's called van der Waals equation of state. If you Google it, it'll be in front of you in about 10 seconds. And let's go on to the example. Oh yeah, before we get to the example, just a piece of terminology. The set of values for the things in the equation of state are called the state of the gas. In other words, what sorts of conditions is the gas being subjected to? If you describe all of that, it's the state of the gas. So we have here a cylinder with a piston in it. Hold on a second. If you want a little help visualizing this, we're talking about something like a cylinder in an engine, actually, but this thing here has the advantage of being transparent, so you can see what's going on inside of it. You've got some gas enclosed within this cylinder, and the volume can be adjusted by pushing or pulling on the piston. Okay, compress the gas, expand the gas. And so that's what's going on in this example here. So now I've messed up the focus. Okay, got it back. In the original state, we see this cylinder here has been fitted up with a thermometer and a pressure gauge to measure what's going on inside of there. This is supposed to be the piston seen in cross section. And here's what the gauge says originally, and here's what the thermometer says originally. You then pile some weight on top of the piston or push on it or something to squash the air. Doesn't say what kind of gas is in there actually. Might as well be air. I don't think it affects the answer to this particular question. Anyhow, you push harder and squash the gas down to half of its original volume. So the question tells you that the pressure gauge now says 125 instead of 0. And the question is, what does the thermometer say? So we have here two states, before and after. Each of those two states obeys the equation of state. So I can write down PV equals nRT for this. I can write down PV equals nRT again for that. And then between those equations, I can solve for the final temperature. So that's kind of the general description and details here in front of you in a moment. So while in the original state, the gas obeys PV equals nRT, then later on, while in the final state, the gas obeys PV equals nRT. To combine these two equations, well, there's more than one way you can work your way through the algebra, and I'm not sure one way is necessarily better than another, but the way I'm going to do it anyhow is to divide the one equation by the other. Incidentally, n does not need a subscript. There isn't any n1 or n and n2. N doesn't change because we're assuming that the cylinder does not leak. The same amount of gas is still in there in the end. And of course, R being a universal constant, The only way that's going to change is if you're living in some science fiction story and pop into some alternate universe. So N and R remain the same before and after. So I took this equation over here and I divided both sides by the same thing, because it says over here that P1V1 is the same thing as nRT1. So what I've done here amounts to dividing both sides of that by the same thing. And the reason I want to do that is N over N equals 1, R over R equals 1. So those things go away and stop bothering me. And once I've done that, I can multiply both sides by T1, and it's solved out for T2, which is the thing I'm trying to determine. Now, here's where people would go astray by doing things like sticking 20 degrees Celsius in for the original temperature and so on. We have to convert to absolute. The original temperature. Question, oh, should fix the lights. For the original temperature, it said 20 degrees Celsius. (293 kelvins). Same basic kind of thing with the pressure. The original pressure, the gauge said 0, but we need absolute. Since the question says nothing to the contrary, we'll assume atmospheric pressure is standard atmospheric pressure, about 101 kilopascals. In the end, the gauge reads 125 pascals. Add the 101 to that. Got 226. Now, technically, the SI unit for pressure is the Pascal, not the kilopascal. When in doubt, convert to standard units. Not always necessary, but never wrong. But it turns out that all that matters is the ratio, okay? And, you know, if this is 2¼ times bigger than that in one unit, it's still going to be 2¼ times bigger than that in another unit. You could have them both in pounds per square inch. As long as they're both the same, the units are going to cancel out, okay? So I could stick some more zeros on the end of this, but I'm just going to leave it in kilopascals because of that. So final temperature, T2, 293 kelvins. Final pressure, 226 kPa. You see that right on the side of your tires. There's that fine print. They always put the name of the people who made the tires in great big letters, and I don't care about that. I want to know how much air to put in the thing, and they got these little tiny letters on there. And it says something like 44 pounds per square inch, and then in parentheses says 300 kPa. And that's for kilopascals. Anyhow, initially, as for the volumes, the question doesn't actually tell us the volume, but it's okay, because just like with the pressure, the answer only depends on the ratio. We know that V2 equals 1/2 of V1. If you fill in that V2 equals 1/2 of V1, the original volume drops out, so it doesn't matter what it was. So you get your little calculating machine, and you do that times 0.5 divided by 101, and it should say 328. That would be in kelvins. If the question just said find the final temperature, you could stop there. But the way it's phrased, it says find the final temperature reading. It wants to know what the thermometer says, and it's a Celsius thermometer, so you have to take the 273 back off again. And you might be wondering, well, converted from Celsius to Kelvin and then from Kelvin back to Celsius, what if I just left it in Celsius in the first place? Don't these two steps cancel each other out? No, they don't. I invite you to try it with 20 degrees written there, and I am pretty certain that you will not get 55 degrees Celsius. If you do, it's some strange quirk of the numbers that wouldn't work if I changed the numbers to something else. Okay, that is the end of section 12. This is the end of what's on the third exam. I guess we're going to squeeze that in at the last minute just before Thanksgiving. And then there's sections 13 and 14 to kind of fill the time between then and the final exam. But the end is approaching. There is light at the end of the tunnel, and hopefully it is not a locomotive.